Let's take a look at how to work problems 11 through 23 on the 3.2 Achieve assignment. I really like this first one because it's having you think conceptually of how a derivative impacts the graph of an original function. Now, what I want you to keep in mind here are these three facts right here. You know that the derivative gives us the rate of change of the original function. So it's going to represent the slope of the original function at any instant in time. So I know that anytime the original function is going to be increasing, its derivative is going to be positive. The quicker that function is increasing, the higher the y value on the derivative would be. Similarly, whenever an original function decreases, its derivative is going to be negative. And the greater rate of decreasing, the more negative its derivative would be. Whenever a function flattens out, this could be at a maximum or a minimum value or at a value at which it just does not increase. You know that the derivative is going to be 0 at those x value instances. Now, I can automatically quickly eliminate the third graph in this one, and the reason for that is because if you look at your original function here, that original function starts off, it's very flat. So I'm not, and now again, please keep in mind, it's completely irrelevant what the y values are. It's the slope of that function that I'm interested in. I can say, well, it's not really increasing or decreasing to begin with, so it starts off with almost a 0 slope. So then its y value on its derivative is going to start off very low. Automatically, it cannot be the third option. That would be silly. The third option would be a graph that's quickly increasing from the very beginning. And so now I can say, well, all right, its y value is going to start very low, which really could be the first or second graph. Now, when I go into why I know it's the second graph and not the first, notice this, this first graph for the derivative shows that your function is going to increase, 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 increase. It's going to flatten off, and then it's going to decrease forever and after. Now, even though it's still negative, the rate of decrease may be lessening as x moves on, but it is still decreasing. Well, notice here, this function is going to increase till here. Then does it decrease forever? No. So it increases, decreases, increases, decreases. So it's going to have 1, 2, 3 x-intercepts. So please notice here, 1, 2, 3 x-intercepts. I know it has to be this second curve. Now, this region right here before the first x-intercept where it turns barely positive, that's representing this portion of the function where it's increasing. It looks like it increases with a slope of 1 about right here. That would mean this y value here is approximately 1. Where this hits an x-intercept is where this flattens off. Then when this turns decreasing, its derivative has to turn negative. So that's this portion right here. When its derivative hit 0, this function stopped decreasing. Then you can see from here to here, it's increasing pretty rapidly. Well, no surprise, its derivative had to take on a pretty high y value in that point. And then it kept on increasing up until I got to that value. And then after that maximum point, it decreased, which means its derivative took on negative after that. So it has to be that second choice there. When I look at number 12, 12 goes back to a very basic problem where you're just giving a polynomial function and you use the power rule to take the derivative of each term here. So you say, well, the derivative of x squared plus 14x is our 2x plus 14 there. Similar, and I'll go ahead and just expand this out. Similar for number 13, we were asked to take the derivative with respect to x of negative 3x cubed plus 4x squared minus 7x. That's just power rule. And remember, notationally, as soon as you take the derivative with respect to x, that ddx notation must disappear. So our derivative with respect to x answer is going to be negative 9x to the second plus 8x minus 7. Final answer there. For the next one, I like it. It gave it to us in terms of fractional exponents. We were asked to take the derivative again. What I did is I said, well, 24 times 5 over 4. I know 4 goes into 24 6 times. 6 times 5 is 30. I got a coefficient of 30. And then x to the 5/4 minus 1 power gave me the 1/4 power. My next term, I said negative 3 over 2 times 3. That's going to be minus 9 over 2 as a coefficient. And then I'll have x to the negative 3 over 2 minus 1 power for the negative 5 over 2 power. My last term, the constant, just derivative of 4x4. And then I wanted to go ahead and put my answer in terms of positive exponents. I'm not sure Achieve would require it. I would require it on a test. So it's good to get used to doing so. We have 30x to the 1/4. Now, since they used fractional exponents, I kept mine in fractional exponents as well. But this negative 5 over 2, I put that x is in the denominator to the positive 5 over 2 power. And then, of course, plus or 4. For the next one, they give us the original problem in radicals, so you would want your answer in radicals. But before you can get to that answer, you need to really convert the radical expression into a fractional exponents. So I said 7 on the root of t, that's the same thing as 7t to the 1/2 power. Minus 6 over the root of t, that's the same thing as 6 times t to the negative 1/2. Again, square root means 1/2 power. It's the negative 1/2 power since that square root was in the denominator. Now we need to simplify. Or sorry, now we need to take the derivative. We've already simplified the expression. When I take the derivative, the 1/2 comes down, multiplies the 7. I get 7 over 2. T to the 1/2 minus 1 power, that's the negative 1/2 power. My next term, negative 1/2 multiplies negative 6. That would give me positive 3, and then t to the negative 1/2 minus 1 power gives me the negative 3 over 2 power. Now, this is my correct answer, but I want to put it back in terms of radicals, and I want to get rid of any negative exponents. So I know that this negative power here just means that t belongs in the denominator inside of a square root. So I write my first expression as t over 2 on the square root of t to the first. Right there. The next one, I have a numerator of 3 and a denominator that's going to have the square root of t cubed all down there all by itself. Keep in mind the 3 does not move with that t. It's not raised to that negative exponent. So we get our final answer like that. Then several of these last few problems are pretty quick. For number 16, it gives me the derivative with respect to y. So again, just power rule. 6y to the 8th. 8 times 6 is 48. I get 48y to the 7th. The second term here, I would say 2/3 times 18. That gives me the 12. And then I'll get y to the 2/3 minus 1 power. That gives me negative 1/3. Now, since they gave fractional exponents in the original, I can have fractional exponents in my answer, but I don't want negative fractional exponents. So I go ahead and rewrote that first term as 12 over y to the positive 1/3 power to get this as my final answer. For 17, we had one like this in the notes where I give you a combination of an exponential and a polynomial function. We say, well, you just take the derivative of each term individually anyway. So just remember 2 different rules here. The derivative rule for exponentials is that the derivative of any exponential function is simply that exponential function. So the derivative of 5e to the x is 5e to the x. But now this is a power function. It's a polynomial function. So you say, okay, power rule. 9 times 5 is 45. We're going to have minus 45 x to the 8th for that second term. Final answer. For 18, we have 3 terms in there. The first 2 are power rule derivatives. The third one, an exponential function. You know that the first term, it's just a constant. Power rule says derivative of any constant is 0 because that's understood to be 3x to the 0 power. So when you took the derivative, the 0 would come down, multiply the 3, make everything 0. The second term, you're going to have 1/3 times negative 15. That's negative 5. And then you'll have x to the negative 2/3 when you subtract the 1 exponent. Derivative of 14e to the x is just 14e to the x. then if you're wanting to make this a beautiful answer, you'd say, well, I don't want that sloppy negative exponent in there then. No. So that's negative 5 over x to the 2/3. Since the original was in fractional exponent, I kept my answer in fractional exponents. Now, does it matter if we're giving you functions q in terms of r and asking you to take the derivative? No. But what does matter in number 19 that makes it tricky is that we don't know how to handle the derivative of a product just yet. That's actually the next section. We'll talk about the product rule. For us at this point, we only know how to take the derivative of terms when they're not being multiplied, divided, or raised to a power outside of the group or anything like that. So we can say, okay, what I have to do and for number 19 is do the algebra before I do the calculus. So you had these two groups in there, FOILed them out. I distributed the 1 through this second group and got 2r plus 6. Distributed the 3r through this group and got minus 6r squared, and then minus 18r. Up here, I just rewrote in descending power with respect to r and collected the two terms of r to the first, 2r minus 18r minus 16r. At that point, it asked me to find the derivative of q with respect to r. So I can say, okay, power rule of the variables with respect to r. 2 came down, multiplied the negative 6 to get negative 12r to the first. Derivative of the second term is minus 16. And of course, derivative of any constant, as always, 0. Now, that continued to be a theme for 19, and then same thing in 20. 20, they give us, or they gave me, a function s in terms of t. So the problem with this, though, is it is certainly in a horrific format to try to take the derivative with our current skills. So what I showed here is that, first of all, if I'm dividing two terms by one term, that term in the denominator distributes to both terms in the numerator. Now, not only did I do that, but I also said, well, I don't know how to take the derivative of the group 14t to the 1/2. So I know that that means 14 to the 1/2 times t to the 1/2. So look at what I did with this denominator. When I distributed into the first term, the 1, I said it's going to be 1 divided by, this gives me the square root of 14, and I could say times the square root of t, but since I know I'm going to need to take the derivative, I went ahead and just said, well, let's call that t to the 1/2. Now, this is better format than the original. For the second term, I went ahead and multiplied the 2, and I said, well, that's just going to be minus 28t divided by that same denominator of the square root of 14t to the 1/2. Now, whenever I'm working this, I can say, well, it's still not in a format where we can take a derivative. We don't want variables in the denominator. That's okay. If you have a t to the 1/2 in the denominator, then you have a t to the negative 1/2 in the numerator, or out multiplied beside the fraction. In the second one, I left my 28 over the root of 14, and I know t to the first divided by t to the 1/2 gives me t to the 1/2. So now at this point, I am ready to take the derivative. I can go in and say, well, the derivative of that first term, negative 1/2, comes down and multiplies this. I'll get negative 1 over 2 root of 14, and then t to the negative 3 over 2 power. Now, for the second term, minus 1/2 comes down and multiplies this. Well, 1/2 times 28 gives me just 14, and I'll have 14 over the root of 14. T to the 1/2 minus 1 power gives me t to the negative 1/2 power. Now, this is a correct derivative answer. It's just not in good format. So what I wanted to do to get it in good format is I needed to understand that these negative exponent means t belongs in the denominator. This first one is t to the 3rd power inside of a square root in the denominator. So I can just say, well, that t belongs in there with the root of 14, and it's going to be a t cubed in there with it. That's where that step came from. Now in the second one, I simplified. I said 14 divided by the root of 14. I know 14 is the root of 14 times the root of 14. So that root of 14 in the denominator would cancel with one of the root of 14s in the numerator and leave me the root of 14 in the numerator. And then t belongs inside of a square root in the denominator, so I just have the square root of t in the denominator. That's the best answer I could get to in that case. Now, those of you who want to rationalize problems, I would rather you not. You can if you insist, but it is not a good practice, I promise. Now, you can see this is what I did for number 20 and achieved like the format of the answer that I just showed you. For 21 here, it gave me a function p of v, and it said if p of v is equal to 3 over v, and we're trying to evaluate this dp dv such that v is equal to -5. Okay, that's no problem. But before I can say it's no problem, please note I did have to rewrite the original. I can't just say 3 over v. It's going to be 3v to the -1. Now the power rule says bring that -1 down, multiply it, then that v is going to be to the -2 power. So I can say dp dv is -3v to the -2. So I'm supposed to find dp dv and evaluate it such that v is -5. So you just plug a -5 in for v in that denominator, and you'll have -3 divided by -5 squared gives me -3 over 25. Pretty nice. The next problem was pretty much the same thing. It gave me r as a function of w, and it asked me to find dr dw such that w was equal to 11. Well, before I can find and evaluate that, I first needed to find dr dw. And I can say, well, I know that w is a variable that's raised to an irrational exponent. Okay, the power rule still applies. I bring that irrational exponent down, multiply it by 2, and I get my -12 pi w to the 1 less power, which means it's raised to the -6 pi minus 1 power. Now I need to evaluate that function at 11, and Achieve wanted me to keep it in exact notation. So the only thing you can do is plug an 11 in where there's a w and leave your answer as that. You cannot simplify beyond that. So dr dw evaluated such that w is 11 is -12 pi times 11 to the -6 pi minus 1 power. And I believe that's precisely the way I entered it on Achieve. Let's see here. It is. I left the parenthesis for the 11 and then showed that that was raised to the -6 pi minus 1 power. Now for the last one here, they're giving you multiple letters in a problem. And I say multiple letters because we can only take the derivative with respect to one variable. So only one of these can be the variable, and it specifically says let capital R be the variable, and small r is, it's just some constant that we don't know what it is. Okay, no problem. Then I know that the derivative with respect to capital R is going to give me lowercase r to the 5th times capital R to the 6th. So I take the derivative of this term here. This is just its coefficient. How do I take the derivative? Well, the power rule says bring any exponent down, multiply it by any coefficient, and then decrease the power on the variable by 1. So that gives me 6r to the 5th times capital R to the 5th. Final answer. A little bit of a strange problem, but I like it. Hopefully you do too. And that's the end of that homework assignment. Starting up next, more fun begins. So this power rule, kind of basic, kind of easy, not too much to it. You just say, bring the power down, decrease the exponent by 1. No big deal, John. No, it's really not. Exponential functions, even easier. You just leave it alone. Now, in the next section, we're going to get to product rule and quotient rule. Things start getting a lot more cool.